reaction set of alkoxy mercuration demercuriation. So if you remember, this was a Markovnikov addition to an alkene, which produces an ether. So it is still a valuable kind of way of producing ethers. So we remember yesterday we talked about how you can symmetrically make ethers through some acid and heat. You can do that through an SN2 type pathway. And then you can also use the Williamson ether synthesis to use an alcohol and an alkyl halide or something with a leaving group to make a non-symmetrical ether that way, also through SN2. And here we have one that you learned about last semester, or whenever you took OChem last. This process essentially was you had an alkene, you'd give it some alcohol along with your mercury with the acetates on it, and then you'd demercurate with your sodium borohydride, and you would end up getting your alcohol as I've got too many of these. You'd get your alcohol there on the Markovnikov side, the more substituted side, right? So that's one more way to make ethers out of things. So whatever your particular alcohol that you'd use in your alkoxy mercuration reaction, that's the ether you'd make. So if you wanted to use phenol, for example, that's the benzene with an alcohol on it, or ethanol or whatever, you could make an ether this way as well. So that's kind of our third way to do it. So this one, though, is a bit more complex, but, it works great if you already have an alkene. So basically, kind of in summary here, if you're looking at a symmetrical one, you can make it from the alcohols. You can take your ethanols, blast it with some heat and acid, and you'll end up with your nice symmetrical ether. You can do the Williamson, where you have alcohol plus, what should we say? Let's say alkyl halide. Or some similar electrophile, right? So if you had, for example, I don't know, we're going to have isopropyl alcohol plus, I don't know, what's our favorite alkyl halide? I don't know, ethyl iodide, why not? Same thing, I think we use that as an example. Some sort of base in there, and you will end up getting your handy dandy ether. And then kind of our third one is the one we just talked about. And so that one you're going to have, by the way, actually let me move this one down. I wanted to also include on this little summary bit that your electrophile must be you'll want it to be either primary or secondary for this reaction. So the alkyl halide in this case. Your alcohol does not matter as much. You can have tert butyl alcohol, you can have phenol, or whatever, but you've got to have your electrophile be either primary or secondary. So because it is SN2, you're not going to be able to get anything happening if you have a tertiary one or an sp2 hybridized one. All right, and then, I guess I should mention that, again, unlikely with tertiary ones. If you have a tertiary one for your symmetrical one, you might end up getting elimination instead. You might go through an E1 pathway instead if you go through this sort of process. You could potentially make it, but unlikely. So we'll see. So just remember, elimination is competing here. Okay. And then with alkoxy mercuration, you're going to take an alkene. Let's just say... No, this is just really ugly. Let me try this with a better... There we go. What alcohol shall we use? Let's use methanol, because why not? If we do that, we'll end up with some sort of mixture of, oh gosh, this is disgusting. Okay, let's try it this way. You'll have your alcohol, you'll have this fun stuff there, your substituents are still there, and you'll have all this sort of racemic fun happening there. So just so you know, you will end up with some racemic mixture in that. Okay, so I guess another note to have here is that Stereochem will follow SN2 rules for your Williamson ether synthesis. Whatever your alkyl halide was, it will be inverted in the final product because it's SN2. Cool. So those were our kind of 3 ways to make ethers. All right, and then fun stuff. We also talked about what to do with ethers. Ether reactions. Oh my gosh, that's so ugly. Okay, let me try that again. Ether, there we go. I don't want to say ether reactions because there's only one. Remember, that's acidic cleavage. So you have your ether, you put it with some acid, typically this bromine or iodide. You end up with those two. But remember, if you've got an sp2 hybridized component here, you're going to actually still get the alcohol out at the end. All right, but you'll still cleave it off. Okay, so that was all we did last time. Do we have any questions on those ones? Any of these, I guess, 4 reactions? How to make them? What to do with them? Alrighty. Well then, let's talk about epoxides. These ones are actually much more functionally useful. Do we remember how to make epoxides? Probably not, but we have two ways to do it. First way is to take an alkene and just oxidize it. Oxidation, there we go, that's the word I'm looking for. Typically, the oxidants you'll use for this could be something like this little guy, you remember that one? MCPBA. MCPBA. I guess I should do all caps because it's an acronym. Metachloroperoxybenzoic acid. You could also use peroxyacetic acid, something like that will work. Peroxyacetic acid. Alright, let's take a look. So, with something like this, you give it your peroxy acid treatment, and you end up getting out your epoxide. And what's important to note here, you will have your, if this was a cis alkene before, those substituents still remain cis to each other in the product. So now as the epoxide, they are still going to be cis to each other. They may be wedges or dashes because, remember, since the alkenes are flat, you can go from either side. So, but the important thing is they stay the same relationship to each other. So notice here, that you maintain that relationship between them. So if they were cis before, they remain cis in your product, in your epoxide, and if they were trans before, they're going to remain trans in your product as well. Okay, so just don't forget that you have that there. Do I need to write out what MCPBA stands for, or yeah, I might as well. Peroxybenzoic acid. Okay, so those are two reagents you could use to make an epoxide like this. Perhaps, though, you remember there's another way. Well, actually, you might not know this one, but hey, we'll do it anyway. Who remembers the product you get from this? Way back when you were talking about that sort of thing. What's the product you get out of this reaction? Even just the name is fine. Anyone remember? When you give a halogen and water,
it won't be halogenation, would it?
you're not necessarily just halogenation. We're looking at perhaps this word, halohydrin. you end up with, and here, let's do it where these just methyl groups will make it a little easier. Actually, this is gonna be terrible. Let's do it with a cyclohexene instead. With this reaction, you end up getting in a trans relationship to each other, you get a halohydrin. So you get a halogen on one carbon of that alkene, and you get some alcohol on the other side. Do you remember this kind of goes through a cyclic bromonium ion? Remember, these words might be somewhere in your brain. If we put a base now in this we also get the enantiomer of this, by the way. You throw a base on this guy, and poof. Now you have, let's see, it's going to come in and attack from there, so you're going to have, actually this is a symmetrical one, so you don't really have a enantiomer. So, actually I guess you do. Yeah, you would. So, remember the base will come in, pluck off your oxygen, you'll have it essentially an intramolecular Williamson happening here. So you can have essentially your, once your base plucks off that, oh no, maintained, once your base plucks off that hydrogen there, or what can happen afterwards, you'll end up kicking out your bromine, and now poof, you've got an epoxide back there. So those are kind of the two main ways to do it. So you can throw an oxidizing agent, a peroxy acid on it, or you can go through this halohydrin and then base type of idea. So if you have an acid-sensitive product, you can't do the top part. If you have a base-sensitive product, you can't do the bottom part. So hopefully one of those will be acceptable to you. So, two options there. Now what's interesting is epoxides, due to the ring strain, are much higher energy than ethers. That means that they are more reactive. And if we kind of just take a look at ethylene oxide here, or oxide rain, one of our favorite words, note that because of this ring strain, you have a three-membered ring. Not very happy, right? It's unstable. We're going to see that we have a lot of different things that can break it. So note that both of these are going to be a little bit delta positive here, as your oxygen is withdrawing electron density. So these two sites become, they're electrophilic. And so, as a result, because of that, they are susceptible to nucleophiles, which means we can throw any manner of nucleophiles at various epoxides, and we'll end up being able to react them. So, shall we take a look at a couple of examples? I think so. First one, standard, just, let's say we have a basic solution. Here, I'll even be good, I'll put my lone pairs on. Light blue for my arrows. We end up opening our ring. And eventually we'll just protonate this. If we just have some aqueous space here. Catalytic, blah, blah, blah. We end up with... Oh gosh, I fit it, yay! So that base gets regenerated, and poof, we now have a new functional group. We have 2 alcohols now instead. Note that these are, well, in this case, it's all, sigma bonds and all that. There's not any stereochemistry in this molecule, but those would be trans to each other if that were an option. Because you would invert the stereochem here, because it is our best friend, the SN2 reaction. That seems to be all we're talking about. You thought you were done with substitution reactions. You're not. So, if applicable, the stereochem is inverted, and your nucleophile and epoxide, oxygen, they're going to be trans to each other. So you may invert your stereochemistry at the site of attack, and when you're done with your product, you are going to have your 2 functional groups. In this case, they're both alcohols trans to each other. Again, this example doesn't necessarily have any because they're the same, right? And it's not a chiral molecule. So, but let's take a look at an example. What shall we put on this one? How about we put... Okay. So, we have this lovely... let me redraw it. It's disgusting. There we go. Okay, so we've got this isopropyl group. We have... And then we have 2 methyls. We have 1 methyl on a wedge, 1 methyl on a dash. What nucleophile shall we put in today? How about we do... How about sodium cyanide? Oops, wrong color. If we put in some sodium cyanide here, as an SN2 reaction, oh my goodness, we'll use dark blue for this. Which side do you think this is going to attack as an SN2 reaction? Which side here? Left side or right side?
Side?
Say again?
Left side?
I agree. Why?
Less steric hindrance.
Less steric hindrance, exactly right. So, SN2 reactions, remember, don't happen on tertiary centers. So, we're definitely going to go for the less substituted side. Right. So, here we go. In this case, it's coming in from behind. Oh, I will be consistent. I will use light blue for my reaction arrows. It's going to pop this epoxide open. And remember, we're going to need our nucleophile here to be trans to our oxygen. So in this case, we're going to end up having our CN down here. We're going to end up kicking our methyl group up. And we're going to have still our other methyl in the back there. And I'm just going to go ahead and protonate that H. That's what the water is going to be doing in the second step for this. And in fact, let me make this a little bit better. So now we've thrown on a nitrile onto our group. And in fact, sorry, let me do that in blue again, just so we're very, very clear of where that came from. I'm not even going to draw it. Okay, so there is our nitrile now. So note we've come in from behind. So it may look like these kind of the methyl and the isopropyl are still, well, you know what, they're still wedges. Yes, that's true, but because this isn't a zigzag, it's a straight line, it's actually messed the stereochemistry up, trust me on it. So that's an example of what we can do with this. So a couple things to note here. Again, SN2 reaction always favors your less substituted side because of steric effects. I'll just write that out. Steric effects here. We're going to see later on, sometimes we're going to have electronic effects happening where naughty things will happen. But here we go. All right, let's do it with a different nucleophile. How about we have... And let's just have one methyl group. We're okay there. We don't need to go crazy on this. All right. Let's do this one. What's our nucleophile here? What's this reagent I've put at the top? Perhaps one you've had a lot of fun with last time. And do you remember the name of this sort of reagent before? I'm gonna have to yell at Chalmers and Mrs. O for not smacking you hard enough with learning these things. Remember this sort of thing? This is a Grignard reagent. Essentially is a carbon with a negative charge on it. Light blue, in it comes, pops open your ether. Now we have, oh, that's 5 members. Again, I'm going to just put our hydrogen on there, but that's technically one more step. And we have our unchanged side here. We still have our methyl group pointing to the back. All right, so you can use any kind of manner of nucleophiles you want here. So you have a huge variety of things to work with here. So for example, you can have sodium cyanide, some sort of sulfide, and some sort of alkoxide. So you can make an ether this way too if you really wanted. You can have Grignard reagents, which would be something with magnesium and bromine, right? What else can we throw? We can throw out lithium aluminum hydride if we really wanted. Remember, that's just a hydride source. That is nucleophilic. So you can instead just pop open your thing with H-, just creating a single alcohol. It's not going to have any more functional groups on the other side. But you see here that we can throw in all sorts of things here. So, if you have just some negative salt, if you want to make an amine, why not? Throw in all sorts of nucleophiles. Have fun with it. You can, the better nucleophiles, of course, are going to be localized or negative charges, so lots of these are salts like that. Again, you're going to end up with your alcohol trans to whatever you're putting on here, but it's very useful synthetically speaking because you can now have two functional groups located right next to each other. So starting with something as simple as an alkene, you can say, aha, here's my alkene, whatever it was. I'm going to go ahead and throw in my peroxy acid. Now I've got an epoxide. I'll make them the same. There are ways to make non-racemic ones. You have enantioselective means of this, but I don't think we cover those in this course, so you're lucky. And then you can say, okay, well now I'm going to put in what is our nucleophile of choice. I don't know, let's make, what do we want to hear? Let's throw in NASME, whatever the heck that is. We're going to end up with, sorry, I forgot that, and then we have our methyl sulfide there. So now we have two functional groups that we can do whatever the heck we want with, and we can have these be, really super different. So you talked about alcohols. You can do all sorts of things with alcohols. If you want, you can now tosylate that alcohol and throw something else at it, and now you can have two nucleophiles there. And so this is kind of a controlled way, by the way, this has still got the enantiomer, of placing two functional groups next to each other. So not on the same carbon, but on separate carbons. So this is a kind of like reliable, effective way to introduce, these are going to be vicinal. Remember, vicinal means that they're one carbon away from each other. So you can introduce these vicinally to each other, so to a molecule. Alrighty. Any questions on that?
May you scroll up a bit?
Of course. Is this good?
The one above it.
One above it, okay.
Okay, thank you. Alright, thank you.
Okay, you're good? Okay, in that case, we're gonna do... Yeah.
Can we also see the part that's underneath?
Yes, of course. So here's this one, and then we'll go...
Thank you.
We'll go after as well.
Thank you so much.
Mm-hmm. So, I want to do a couple of, let's say, synthesis problems. I'm going to kind of just put them up, and I'm going to give you like a couple minutes to work on them, and then we'll go over them together. So it's not just me blathering on for an hour and a half each day. And then we'll kind of talk about our last little bit about epoxides then. Okay, so I'm going to scroll down just a little bit more. So just so you can see that reaction there. So hopefully what's interesting about this course is, since you've completed so much last semester about kind of our most simple functional groups, or our most kind of useful ones, I'd say, like, you've learned so many ways to make alkenes, and you've learned so many reactions of alkenes, right? Now we're finally like throwing more stuff at it, so you can actually talk about making molecules rather than just kind of like, well, here's this random alkene and we're going to do one thing to it. And so you're going to see here like the kind of main idea, like the ideal goal for students learning OChem is to be able to do multi-step syntheses with each other. Not with each other. Well, yes, I guess collaboration is good, but with various steps, right? So let's see what we can do. Let's say I want I'm actually going to write these out. And no, let's not do that. And on this one, let's put our isopropyl group. So I want you guys to make this from the alkene of your choice. So, starting with an alkene, I've kind of left it, I have left this molecule in the same way I would write the product of some of the reactions we've just done, where, I've kind of had this horizontal line in the middle, so it's not really a zigzag. That may be a hint for you. So I want you to, you're going to need a couple of steps. We see here, obviously we've only really talked about ethers and epoxides, right? So let's see what you can do. Take a couple of minutes and try and look at this molecule, look at the relationship of the functional groups to each other, and see if you can choose a reasonable starting alkene, and then from there, here we'll even put plus minus on it, it's racemic. Go ahead and give me the reagents that you would use to take your alkene of choice to transform it into this molecule. Alright, so for the next 3 minutes I will just be twiddling my thumbs. If you have questions though, just shout them out. I'll just be waiting. I'll see if there's some more examples I want to throw at you guys. Boring stuff here. We have thiols next. I realize this is not a fair molecule to give you. Should I change it to make it easier? Yeah, I will. I am just changing one thing. We'll just make that a little bit more likely for you guys. So I've just swapped those two. I've made the top one the ether, the bottom one the hydroxy. So hopefully it'll just make it a little bit easier. Well, let's have just maybe one more minute and then we'll take a look at it together. Alrighty. I guess it's going to be kind of hard to share the alkene you've chosen. So, talk me through it. Here's an alkene. What did we put on this alkene? Let's start on the left. What did we put on that? The left side of this.
Isopropyl.
Isopropyl? Okay. And which way did you put it? Just out of curiosity. Up or down?
Up.
Up. Okay. Sounds good. And on the other side?
CH3.
CH3. And which direction?
I just put it down.
Down. Okay. So, if we go ahead and do this, what are we looking at to do next here? I hope I have the room. I might. We'll see. I'll move this arrow over. What are we looking at next? What's the next step in this reaction? Even if you had a different alkene, what's the next step here? Go for it. Oh, we have someone shy. I do see y'all unmuting occasionally. Shall I call on someone, perhaps? And you know that person's gonna be Eric, because I have to pick on him. But, what's the next step here? Go ahead, Ramon.
Could we oxidize it?
Yeah,
Could we
oxidize
use,
it. What would you like to use to oxidize it?
RCO3H.
Okay. Great. And what do we get out of that?
We would get an epoxide.
Mm-hmm. So, in this case, I'm going to just go ahead and put it this way. So, in our alkene here, we had them trans to each other, right? We had the isopropyl and the methyl trans to each other. So in our epoxide here, we're going to end up having those trans to each other. Again, this will be on either side. So, plus minus there. And what's kind of our next step here? What's our next step for this? Alrighty, shall we resort to random number generation? Let's see how many people are here. 21 maybe? Alrighty. Let's do it. Let's find out who's our victim. Computer, choose a number 1 through 22.
Here's a number between 1 and 22. It's 13.
13, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's Melanie. You get to be our victim here. So, what reactants are you going to put in this, Melanie? Poke, poke. Wake up. There you go.
Not sure.
Not sure. Okay, that's okay. So, let's look at it. So, if we take a look at this epoxide here, if we're just going from that middle molecule to the right molecule, what's different? What's in the right molecule that's not in the left?
The OH and the OH.
The OH, yeah, technically, and then the OET, right? Both of those are new things in that molecule, right? But we know that if we're going to open an epoxide, that O, I'm going to do it in dark blue, this O will become our OH, right? We've seen that in all of the previous examples, we end up with an OH because of the O of the epoxide. So even going back up here, again, we have the OH that comes from that oxygen there. So with that in mind, we have now this thing that's missing. So what can we put in? I mean, we have to put this in, obviously, right? Is there a way to make this OET, this ethoxy thing, can we have it as a nucleophile? Is there a way to make an ethoxy group attack that epoxide?
Sodium ethoxide.
Yeah, sodium ethoxide would work just fine. So the sodium ethoxide is there. The sodium is there to make sure that we have charge balancing, but it's really OET minus, right? So we have this oxygen with its negative charge. It's going to be a nucleophile because it's got that localized lone pair ready to go, ready to attack something. And so we're going to go for the least sterically hindered side here. And that's going to go ahead and pop open this ring to give us our product. All right. So, and then just second step water, just to protonate that alcohol at the end. That's what we're looking for there. So this part will end up giving us our OET. Just throw the sodium salt of that in, and poof, now it's a nucleophile, and you can go ahead and have it attack. It's again attacking the less substituted side, so or the less sterically hindered side. So isopropyl is bulkier than methyl, so we're going to go on the methyl side there and get our answer. However, we do have one thing that's not quite correct here. So just remember that if we see that these two are trans to each other, right? And so it's nice to say, okay, well, we've got these two trans to each other, but we have to remember that because this is SN2, we had an inversion happen. And so, as a result, what we need to keep in mind here is that our we need to have the opposite of that in our starting material. So if we had it trans here at the end, we're going to need them to be cis in the beginning. So we actually need those starting materials to be cis to each other. So we're going to need it to be on that side. Oh no, now we have it on our R group. I'm going to just put them actually both down just so it's clearer. And we're going to therefore want this guy to be on a wedge. So that's the one thing there. So just remember that if you want them both on wedges in your product, you're going to need to make sure that they're wedges in the starting material. It seems weird, I know, that one set is cis, the other is trans, even though they are all wedges in all the cases here. Trust me though, if you were to do the stereochemistry on these, you'll see that it does change. So, trust me there. Alright, so it's because we've now, we've knocked that wedge for the isopropyl was actually like kind of pointing down before. With our other thing, we actually knocked it the other way. Or in this case, we knocked the methyl the other way. So, trust me, it does switch. So, just copy the same kind of symbol you see. If you see wedges, make sure your epoxide has wedges. And if they're both wedges, then they need to be on the same side of your alkene. And so, if they're opposite, one's a wedge, one's a dash, then you'll want them trans to each other to begin with in your alkene. Alright. So I think you guys are going to do more of this sort of stuff in lab tomorrow. So you'll have, apparently you guys are going to have plenty of time to do practice problems. So we'll work on that. So, cool. Any questions on that one? Do we see why we chose those reagents and why we chose that alkene? Alrighty. We'll have some more of this, don't worry, in lab. So, but for right now, things to keep in mind when you're looking at your product. Here, you know what, let's just do like 2 examples of this. So let's say we had... let's see, what other nucleophiles do we have here? I don't know, how about bromine? Because why not? If we want to think how to make this thing, well actually we just use halohydrogen, let's not use bromine, that's boring. Let's do, yeah, let's leave it as methyl. So if we had this molecule to start, here, let me move this one over. It'll be the same molecule, don't worry. How might we make this? I'll give you a hint. The middle thing is going to be something that we've seen before. This whole chapter. This whole day, I guess, actually, we've been focusing on it. What's different between our starting material and the end? We've introduced 2 things in here. What's the obvious thing we've introduced?
OH.
OH, right. Now we've thrown it in OH, so that's one thing we've seen. So just things we've added to this. What else is different?
Just the double bonds are broken.
Double bond is broken, sure. 3, we'll say. What else? What else is different here? Don't worry about the stereochemistry. I mean, for right now, the starting material is not chiral, right? And, of course, with all these, we still end up with our racemic mixture, but ignoring the fact that now we have this dash out of nowhere, what else is new here?
Before you rewrote it, didn't you have a bromide at the end?
I decided to switch that out, because
Okay.
you could just do that in one step. You could just put
Okay.
bromine in water, and poof, now you've got your halohydrin. But I wanted to do specifically through the epoxide that we've learned today. So if it's not a bromine, what have I added? What does it mean?
You added a methyl?
Added a methyl, right, exactly. So I've added now an oxygen and a carbon to this molecule. And so we see that, okay, notice that these two, by the way, are also vicinal to each other. So that means they are one carbon away from each other, right? So this oxygen, I'm sorry, they're two carbons away. They're on adjacent carbons. So that the carbon that the hydroxy is on is adjacent to the carbon that the methyl is on. So we have vicinal things. That's going to be your hint that somewhere in this kind of reaction scheme we had an epoxide. So this kind of indicates an epoxide as a kind of, what's the word? I don't want to say intermediate, but kind of an intermediate. As an intermediate, why not? I'm going to put that in quotes because it's not really an intermediate. So, with that, if we have an epoxide intermediate, thankfully we know what those must be, right? If we know we can make epoxides from alkenes, so here we go. There it is. There's our epoxide from our alkene. Right? Because this is going to be racemic, it could be a wedge or a dash. It does not matter, because we're going to get both enantiomers. So either way is fine. I drew it as a dash because we have the dash in the product, and I'm just being consistent with that. But you could put it as a wedge. It doesn't matter. You'll get the same racemic mixture. So, now that we know that, that's going to be our intermediate, right? So, now let's go ahead. So we've taken care of point 3 there. The double bond is gone. So, check. That one's done. We've also essentially added OH, right? We know that that oxygen in the epoxide will become the alcohol in the product. So we've added our oxygen there. So the part that we're missing now is, where did this extra CH3 come from? How might we add a CH3 to this molecule?
Could we use a Grignard reagent?
Use a Grignard reagent, why not? Yeah, so we can say, let's use as our nucleophile. So with many other functional groups we might add, like an ether or a sulfide or the nitrile. We added a CN in one of the previous ones. We just threw a sodium on it, right? And now we had a nucleophile. For carbon nucleophiles, remember, they've got to be Grignard reagents or Gilman reagents, as far as we know right now. So if we're going to add carbon to our molecule, we're going to need, for our purposes right now, a Grignard reagent. And so that's going to be the carbon part that you're adding, as well as our dear friend Migbur, the magnesium and the bromine there. So, with that, now we can say, aha, if that's our nucleophile, that CH3 minus is going to go and attack. It's going to attack that less substituted spot, and poof, now we will end up with our product. So our reagents then, so step 1, we're going to have MCPBA, or just kind of generically some peroxy acid. That's step 1, to go from alkene to epoxide. And then, since we said we're going to add our CH3 Big Bur as our Grignard Reagent nucleophile, that'll be kind of like step 1 within it, and then we just need water at the end to protonate our alcohol. So those would be the steps that we would go to make this molecule from that alkene. All right, so hopefully Professor Chalmers will do examples like this, where you're given a product, potentially given a starting material as well, and asked, okay, how are we going to get from A to B to C? And so these sorts of things you'll also find kind of in your textbook in the back of the chapter as kind of extra problems. I would definitely suggest doing those. I'm not sure if there's an SI session for this class, because I got put on as the lecturer kind of late, so I didn't set anything up, but I don't know if Chalmers has. Maybe good to ask him as well, because that'll just be more practice that you can do as well through the SI program, where there's going to be kind of tutors to guide you through examples. And it does help to hear the information from people other than myself or Professor Chalmers. You know, we tend to be, we think a little differently. So, you know, it is helpful to have your fellow students talk about it, because they may be able to like frame it in a way that's easier for you to understand. Because, you know, I just throw out nucleophile, electrophile, every other word, right? And, you know, that may be just kind of being like, oh crap, what does he mean by that? You know, it's, it may be easier as well that way. So, cool. All right, so, in summary of what we've done here with this problem.
Professor?
Yeah, what's up?
Sorry, can you explain again when you use the Grignard reaction?
Sure. So, in chemistry, there are not as many ways to make carbon-carbon bonds as there are to make carbon, oxygen, or whatever other atoms. There's just a few of them. And so what we've learned so far in last semester's OChem, the main way for us to add carbon to a molecule is to use a Grignard reagent. So a Grignard reagent they are going to be some sort of alkyl halide like this. So I've got methyl bromide here, which, if we were just draw the Lewis structure, you know, is something like this, right? We have all these nice covalent bonds. This carbon actually is not going to ever want to attack anything. It's already got its octet, it's happy, it's good to go. It might be attacked, actually, because bromine is a leaving group, but it's never going to attack anything. And by attack anything, I mean it's not going to go ahead and like stick itself onto a different molecule. So it's not common that way. But they found, this Grignard guy who won the Nobel Prize for this, found that if you throw magnesium in this mix, what happens is that magnesium actually will insert itself in between. So, if we think about this, magnesium has got 2 valence electrons, right? It's in group 2. One of those, it's going to kind of say, okay, you bond here between carbon and bromine. Let's go ahead and take one of those electrons there, and the other electron there. It's going to just kind of insert itself. And so now, our molecule is actually ignoring 3D structure. it's really now essentially an ionic compound. Really, it's got some covalent character, but this is one way to describe it. So we have now this carbon with a negative charge, stabilized by the magnesium and the bromine there. So it's kind of like a mix between ionic and covalent, but we'll say that it's happening there. And so as a result, this becomes a nucleophile. So a nucleophile means it's got a negative, or ideally nucleophiles have localized electron pairs, meaning those electron pairs are not stabilized by resonance or by some other, means of stabilizing them. And so they're ready to say, I'm kind of unstable. Let me find somewhere to connect my lone pair to some other molecule so that I can become stabilized again. Because carbon doesn't want to be negative, right? It prefers to be neutral. So, as a result, we can use this to say, aha, this carbon is going to go and find something that's slightly positive and latch itself on there. So, if we have, for example, an epoxide, and I'm just going to put some other bit there, this essentially, CH3 with its lone pair, stabilized by these two, is going to say, aha, there's something positive. I'm negative. I'm going to go ahead and attack. So it's going to go ahead and latch itself onto that carbon that's slightly positive, because the positive and negative attract each other, right? And as a result, it's going to break that CO bond. That's the CO bond is the weakest bond in this structure, not only due to the ring strain, but because carbon and oxygen, since it's a polar bond, it's going to be a little weaker. So that's going to pop open this ring. And so as a result now, we have our, we'll end up popping this open if we just give it some water, and we keep our other methyl there. So as a result, we've just now added this CH3 to our molecule, using it as a Grignard reagent. Okay, so it works like any other nucleophile, got that negative charge ready to attack something that's got a positive charge, or a partial positive, and so it's happy to latch onto this molecule. So now we've made a new carbon-carbon bond. So, this part of the molecule was our original epoxide. Fix that. We've now added a new carbon-carbon bond here. So that's how we've done it. So whatever your new carbon substituent is, in this case it was just a methyl, that's the only thing that we added. As we saw here, 0.2, we had added CH3 to this molecule. I could have added any carbon. I could have said I'm going to add an ethyl group, or benzene, or whatever. And the way to do that is to use it as a Grignard reagent, meaning you just stick magnesium and bromine onto it, and now you can use it as a nucleophile. So if I wanted to add benzene, well, I could just say, well, here we go. If I have benzyl bromide, stick it with some magnesium. Typically you'll use, by the way, an ether as your solvent. You now will get essentially your negative charge there stabilized by the magnesium bromide. Now you can use that as a nucleophile. If I wanted, I could go ahead and now attack some electrophile, something positive, and there we have it. So now I can use that as a nucleophile. So if we want to do that, if we want carbon-based nucleophiles, you want to use them as a Grignard reagent. So you might say that this one is phenyl magnesium bromide. Just like before we had CH3 MgBr, this is just phenyl of the same thing. So Grignard reagents are a way to make new bonds there. Okay, hopefully that clarified that a little bit. You may want to go back to, when did we learn about Grignard reagents? I don't even remember. Maybe in, which chapter would that have been? In Wade, I don't remember. But it may be helpful to just maybe like take a look at the index and see the first time it's introduced, so you can go back and review that section. So, okay.
Yes, thank you.
Cool. All right. So, just in the interest of completing this stuff on time, just so you guys can talk about it in lab tomorrow if you need to. There are other ways to break epoxides open. If you wanted to use an acid, you can do that. You can say, okay, here is my epoxide, our dear friend HX, just like a standard ether, and you'll end up with your, you'll end up going this way with it. So how this mechanism works is you've got HX. You're going to go ahead and protonate your epoxide. And so now you have this little thing. Oops, totally not a lone pair there. So now we have our positively charged oxygen. That's going to make this like even less stable than it was before, right? So epoxides are already relatively unstable because of their cyclic three-membered ring, a lot of ring strain there. But now, because it's fully positively charged, it's going to really take a lot of electron density away from these carbons. So lots of electron density. So these become like super partially positive, because that oxygen is like, I'm positive, I hate being positive, I'm going to be sucking up extra electron density. And here is our good friend halogen X is going to go ahead and come on in and pop open our ring. And lo and behold, we now have our opened epoxide. So 2 little steps here. So in fact, I'm going to clarify this arrow a little bit because it's just not as nice as I would like it to be. So this is going to attack that carbon right there. It's going to pop open the ring, and it could attack either carbon. And in this case, it's symmetrical, it doesn't matter. Although, here's the although part. So we can just open it, pop it open with some acid, and we'll have our conjugate base go ahead and attack. So if that's a bromine or whatever, now you have popped that open. Couple things to note here. Oh, that's so ugly. Okay, well, whatever. So, if you have these two, you're going to see that with this one, your X will prefer the less substituted side. This is again due to steric effects. But it turns out, so it's going to go ahead and attack there, for example. With the other one, you could go either way, because it's symmetrical, there's no difference. So, but in terms of regiochemistry, where something is going to attack, you're going to see that with a primary versus secondary, the primary will be attacked. But, weirdly enough, if we've got this one now, your thing will actually attack a tertiary side of your protonated epoxide. Oh my gosh, I'm missing so many lone pairs. Shame on me. Okay, there we go. These are all positively charged. What's curious is that your nucleophile is actually going to attack the tertiary one. And the reason for that is actually electronic effects. So while the other side is less sterically hindered, that's certainly true. Remember that the tertiary carbons can accommodate positive charges more easily. Positive. And that's due to hyperconjugation, right? So, as a result, that carbon on the right, the tertiary one, has a greater partially positive charge, and therefore is more attractive to the nucleophile. So, if you're going to be using acid to open up your epoxide, previously we used just nucleophiles, right? And then we'd throw some water in to hydrate things. If you wanted to use an acid to break it up, there's just a few things regiochemically speaking. So, if you have a primary spot versus a secondary spot, you're going to put your nucleophile on the primary spot. All right, because the secondary spot is sterically more hindered. However, if you have a primary versus a tertiary spot, the tertiary one is going to take it because electronically it can hold a much greater positive charge than the primary carbon. So if we think about this, we've got partially, I really should use different colors. We've got our partially positive here. This one is going to be much more positive. So, oh, that looks like some, okay. There we go. So, as a result, you're going to have a greater propensity for your nucleophile to attack the tertiary carbon there. All right, so we're pretty much out of time. We'll continue this last bit on Monday. And then on Monday, last bits of epoxides, and then we'll talk about thiols and sulfides. Those are really quick. There's really not much to talk about there, but we'll have that on Monday, and then we'll start talking about conjugated systems. So, if you have questions over the weekend or whatever, since we are out of time now, throw them in Discord to say, like, hey, can you explain this tertiary carbon business again? And either I will just explain it, or I'll say, here's this YouTube video I found that is good at explaining this concept, and then I'll give that to you. So, something like that. Okay? Cool.
Thank you.
Yeah. All right.
Thank you, Professor.
Sure thing.
Thank you.
All right. Take
Thank
care,
you.
everyone.
Professor.
See ya. Yeah. Oh, shoot. You're right. Elena, good point. I better make that. I meant Wednesday, of course. So, Monday we do have a holiday. Good point. So, I'll see you Wednesday instead. Thank you for that. Hooray, holiday. Okay, great. Take care, everybody.